You all use tunnels when you use the VPN. We will see that it exists also in lots of other contexts. So a tunnel, some terminology. Tunnel is also called encapsulation. And it occurs whenever we put inside a layer packets that are not expected to be there if we follow the hierarchy of layers. For example, if we put an IP packet in UDP, we do things the other way around, right? The UDP packet should be in IP, but not the other way around. Or a max layer packet in UDP, or an IP in IP, etc. In theory, of course, in the clean theory, it should never be used because the layer theory says the transport is above the network is above the link layer, etc. But in practice, there are at least three major reasons that we will see for using them. One is security, another one is the use of private addresses, and the third one, which will be very important in the transition phase, is the interworking between IPv4 and IPv6. Let's see a simple example. Assume you are deploying on two different sites, two networks, and you don't really need a web server or anything, just your private network. So you don't bother giving public addresses or buying and using public addresses. So you have two sites, and at A and B, you have routers that are connecting to the public internet. And inside each of the sites, you use private addresses here. And now you would like to interconnect the two. That's the common problem that many companies have. We use private addresses inside a site. EPFL has multiple sites and uses private addresses a lot. How do we interconnect the two between the two sites here? So one simple solution. Of course, we cannot simply put a router here and connect there. One simple solution would be to put a NAT. If we NAT all the addresses here, then we can go via the public internet. But by NATing here, we make this part of the public internet, which is perhaps not what we want in this case. So what we will often do is what is called virtual private networks. The very first step in doing a virtual private network is to configure what is called a virtual interface at the router A. What is a virtual interface? Where it is simply the knowledge of a destination IP address 22222 here, on which we are supposed to send every traffic that goes out of this virtual interface here. So here we configure that the address 1111 is attached to is connected by this configuration to that other address. And then any packet that goes from this to that, we can simply put it into an IP packet that goes from 111 to 222 over the public internet here. So IP packets from S to X, for example, here are routed inside the private domain. Then when they reach router B, B will say, oh, my default route or my route to the rest is to A here. And it's not a physical interface like we have in Mininet or in your laptop. It is an interface which is built on top of a physical interface and by using encapsulation. And the operating system practically always will show this not as an encapsulation, but as another interface, as if there would be another physical interface at router B, the physical interface that it has to connect to the internet, plus another one which consists in using IP in IP. So for example, if S sends a UDP packet, so the app at S is using UDP, talks to X, for example, or using whatever quick or something like this, and we do a Wireshark at this point here, what will we see? Closing the poll in a few seconds. closing. Majority says A, but this is not correct here. It's true that the IP destination address is 111, but the protocol is not UDP. The protocol will be IP. We are carrying an IP packet inside an IP packet. So this is why we will see this strange thing. In the IP header of the packet here, we will see next protocol, if it's IPv6, or protocol type, if it's IPv4, which says, well, it's again IP. So we'll have an IP packet inside an IP packet. If we do the varchar, we will see two IP headers. And of course, the IP header that is inside the inside the packet is an IP header of the blue domain. So we'll have destination address 10.111. That is what encapsulation is about. It's as simple as that. In practice, it's a bit more complicated for two reasons. First, IP in IP often doesn't work because many filtering routers don't like whatever they don't know. So they typically accept only UDP, TCP, and ICMP. So if you put something else, they will kill it. That's a bad reason, but that's a practical reason that exists. So in order to circumvent this problem, what some software does for that kind of tunneling is to put UDP into IP. So because firewalls don't kill UDP, at least by default. So what is often done is to have a UDP header that contains another protocol that's somehow, it's called L2TP/PPP. That's a protocol that is practically useless, but is inherited from the MAC layer. So we can ignore it. And then it will contain here the blue packets that will again have an IP header, a UDP header, and the data. In practice, we want more than that. The motivation of Homer was to interconnect the two sites by making them private, going through the internet, but not being exposed to the internet. Now, if you send your data in the clear through the internet, you're still exposed because people might do a Wireshark and split some of the cable, for example, put a repeater, analyze all traffic, and gain access to all information that you're sending. So in practice, you want to encrypt everything that you send over such a tunnel. So it's not so difficult. We've seen how the classical encryption is done in all the contexts we've seen so far. It is by using TLS. That's a classical way of doing. You can do the same thing with another name. It's called IPsec, IP security. It is encryption and authentication that is performed on something that's natively contained at the IP layer. TLS is for something that is contained inside TCP. There is also a version of TLS that works for UDP, but it's fairly rare. Normally, we use it over TCP. You can also, of course, encrypt the content of an IP packet, and the set of standards for that is called IP security, IPsec. So IPsec specifies the header format for containing the information that will be used for carrying the encryption here. So if we use IPsec and the encapsulation method I've used, if we do a Wireshark, we will see an IP header with a destination IP address, a UDP header, a PPP header that is essentially saying what is the next protocol type, which will be here IP security. IP security will contain information about the cipher in two forms, typically at the beginning and at the end of the packet, and then the packet itself, which is now encrypted. Now here we are truly protecting the traffic here, because any attacker that will read this will simply see that there is a packet being sent to the other end of the tunnel. So the only information you can gain is the amount of traffic, the frequency and the speed and the traffic profile between A and B, but the content will be completely encrypted. I mentioned that we can do encryption also with TLS. So not surprisingly, there is an alternative way of doing this, which is using TLS. Now, instead of doing encrypted packets inside IP. You can do encrypted packets inside TCP. This is what software like OpenVPN does. With OpenVPN, A and B will establish a TLS connection. So they open a TCP connection, then a TLS connection. And then inside this TCP connection, all the traffic from A to B is sent here. Encrypted, of course, so it will have different headers, but the effect will be, from the encryption viewpoint, will be the same. From a traffic performance, it might be a bit different. If we have a TCP connection from A to B, this TCP connection is traffic controlled. So if there is a loss somewhere on this connection, the rate at which A is sending to B will be reduced, for example. So the rate of the entire tunnel is controlled. Whereas if we use this method here, the rate of the entire tunnel is not controlled by TCP, which is good or bad, depending on the situation where you are. That's also a major difference between the two. So if you use the VPN or VPFL, you are, for example, sitting at home over your Wi-Fi network, then you have access via your Wi-Fi infrastructure and Swisscom, Sunrise, or whoever is serving you to a VPN router, a VPFL, that also implements IPsec. And this is the kind of things you can see. This is an IP config I did on a Windows PC a few years ago. This is what you would see. You would see that there are two interfaces. That's my physical interface on the home network, and that's the logical interface that pretends to belong to EPFL. I have received here an IP address of EPFL. The IP address, if you look at it carefully, it belongs to the subnet 83 of EPFL for IPv4. And now the question is, of course, A will send all traffic that goes to, at least to any, I mean, most systems will recognize as destination address whether it's in this domain, in which case it will be sent to this interface. Otherwise, if it doesn't match anything here, it will be sent to this interface. So all traffic to EPFL servers, for example, will go via this way. But when the EPFL server replies to me, the EPFL server believes that I am on EPFL sitting on the subnet 83. How does a packet find its way to me, given that I am not on the subnet 83? Closing in a few seconds. Closing. And the majority says A, which is the correct answer. Now, the only difficulty in the return path is that the packets will reach the router R. A router R will do the standard thing and will need to find the MAC address of me here, which of course doesn't exist or is completely irrelevant. So what it needs to find is the MAC address of the VPN router. And we've seen that there is a solution for that. VPN router does proxy R. That's exactly the standard use of proxy R. I am here on the subnet that is on the other side of the VPN router, and that's how things must be if I use a VPN. There's no other way I should do it. So VPN routers typically comes with proxy R. That's for the VPN tunnels. Now, tunnels exist in a different setting in the context of the interworking between IPv6 and IPv4. We've discussed this already when we talked about application layer gateway. With application layer gateway, we discussed the interworking solution. How can somebody who speaks IPv6 connect to someone else who's speaking IPv4? We've seen that one way is to put an interpreter in the middle, which is an application layer gateway that will translate IPv6 to IPv4. Here we're discussing something different, which is how can I have access to IPv6 to talk to another IPv6 machine when my infrastructure gives me only IPv4 or vice versa. It's called like-to-like access here. For example, that's the problem you have, or we had last year, when EPFL Wi-Fi was supporting only IPv4 and not IPv6, and we want to do labs and things on IPv6. Well, there is one solution, which is called tunnels, and in particular, tunnel brokers. So a tunnel broker is a company that has IPv6, an ISP typically. Hurricane Electric is the one we used last year. Hurricane Electric agrees to give to anybody. You can go to this website and you will obtain from Hurricane Electric a tunnel that allows you to connect to their IPv6 part of the internet over IPv4. So if you have IPv4 only from your provider, and you have at home a little network that runs IPv6, and say you want to test a number of things with IPv6 only, then you will obtain this tunnel here and go to the public internet. So what does Hurricane Electric give us? Well, it gives us first an IPv6 address to which we can connect, but it needs to give us more. It needs to give us an entire prefix, because I need probably to have more than one IPv6 address in my own system. So they give us, for example, a 64-bit prefix. That's the practice last time we tested it. So this prefix is allocated to us here. And therefore, inside my local domain, I can run OSPF or RIP or manual configuration. I can allocate my addresses within this prefix here. I also need to know other things. I need to know the IPv6 address of the final destination here. And I need also to know the IPv4 address of the final destination. I need to know this because I will need to configure my router here with a tunnel, but I need to know the final address here. Then once I have done that, I create, like before, a virtual interface in my machine here, which is called a tunnel interface. That corresponds to the IPv4 final address here. That means on this virtual interface, any packet that you put will be encapsulated inside an IPv4 packet with this destination address here. That leaves a number of questions, like from the viewpoint of IPv6 routing. Now, this router here, when it has an IPv6 packet to send, it fits to be sent locally, then it will know where to send it. Otherwise, it needs a default route, and the default route is exactly this address here, which means that the default route of this IPv6 router is the IPv6 network of Hurricane Electric. So Hurricane Electric is abstracting into its IPv6 network all traffic of all customers who use those tunnels here. And for anyone else who is using this, for example, if Lisa speaks to Homer here, then Lisa will have the impression that Homer is sitting on the IPv6 network of Hurricane Electric, because this prefix here belongs to the set of addresses that are allocated by Hurricane Electric here. So you will de facto be as if you would be sitting here. That's a bit experimental for debugging, for testing. Why? Why do I say this? Well, imagine you want to go to the IPv6 server of a pizzeria next door to you, which is sitting here. Then your traffic will traverse the world to go to Hurricane Electric, encapsulated in IPv4, to return back via another path if this pizzeria is working on IPv6. So the path that you take will be extremely long. So local traffic will have to cross the tunnel here. Also, obviously, if you're a large company, like if you're EPFL, for example, you don't want to put all the traffic of EPFL into one tunnel because you have no guarantee on the speed at which you will be served here. Probably this network node B is serving hundreds of thousands of customers, so it's giving very little throughput. So from a performance viewpoint, it will not be top, but that allows you to test IPv6 connectivity for free. And that's what the solution we used until last year, because EPFL took 10 years to deploy IPv6 internally. So if we're in this configuration and we do a Wireshark at 1, when Lisa is sending a packet to Homer here, what will we see? I close the poll in a few seconds. Closing. There's a short majority for D, which is the correct answer. There is no encapsulating packet here. There is no encapsulation inside here. Encapsulation is here, but not here. So here it's a native IPv6 packet that will be put into the tunnel by B, but here there is no such thing. What is the implication for path MTU? Is there an implication for path MTU? That's the next question here. So if there's a TCP connection between those two ends, what is the path MTU that this TCP connection will be able to use? Closing. And the majority says B, which is the correct answer. So here I'm creating an IPv6 packet. What's the maximum size of this IPv6 packet can have? Locally, 1500 bytes. But then this IPv6 packet will be put inside an IPv4 packet, which consumes 20 bytes of header if there is no IPv4 option, which is not certain. Most of the time there is not, but not always. So in the best case, we lose 20 bytes here. So if this packet is 1500 bytes, it will not fit in an IPv4 packet. So this packet, probably tunnels do not accept to do fragmentation. So this packet will be discarded with a ICMP message saying packet too large. Yeah. So it will be this in the best case. And if you want to be safe, you probably want a value that's below by allowing IP options to be done. The tunnels are an experimental way that's provided by some ISPs to get things going. There is a more systematic use of tunnels, which is called 624 or 6RD, which we also used at EPFL for some years. And 6RD is probably what is used by you and me at home from Swisscom or Sunrise or others when we use IPv6 from home. It uses the same idea of a tunnel, but probably the first thing it will do, the B part of the tunnel will be a carrier grade tunnel endpoint, so to provide good performance. And the other part, which is more interesting, is that the choice of addresses will be completely automatic. So let's discuss 624. How does 624 work? Well, 624 reserves two things: a block of addresses in the IPv6 domain, which are called the addresses that I read 2002, even though this is not the number 2000. That's hexadecimal 2002 slash anything else. So the is reserved for, so the block /16 is reserved for 624 here. And why is it reserved? Well, the idea is that to any IPv4 address, which is 32 bits, you can create a valid IPv6 prefix by concatenating this and the 32 bits of the IPv4 address. That's a way to embed IPv4 into IPv6. Surprisingly, this was not designed by the inventors of IPv6. When IPv6 was designed, they decided very much the Apple way, when Apple moved from Intel to another Apple processor or vice versa, from Motorola to Intel, they say, no, we're not compatible. We'll make some emulation software, but it's not compatible. Here, it's exactly the same. So IPv6 and IPv4, as we know, are not compatible in the sense that an IPv6 is not a new version of an IPv4 packet. So all systems, if there would be something compatible, if there would be a compatibility framework put in place, you would have old systems that support only IPv4 and new systems that would automatically support IPv6 and IPv4, because an IPv6 packet would be just a new version of IPv4. We have such things for AS numbers, for example. We discussed AS numbers, but they have been extended recently because with the growth of the internet. So the size of an AS number has been double. But of course, BGP with old and with new AS numbers continues to work. So for some reason that I'm not fully able to find good reasons for it, for some reasons, this is how it is. So one way to fix it is this 624 way. So here, if I am at home and I have only IPv4 connectivity, because my provider, old style, provides me only IPv4, then I will automatically obtain IPv6 addresses by concatenating my IPv4 address to this one here. So typically, when we use IPv4 at home, we have one IPv4 address, multiple devices. So that solves the problem of getting an entire prefix here that I obtain. That's the first part of the story. The second part of the story is I want my home router to create a tunnel to some other endpoint, very much like we did before. For that, if we use the Hurricane Electric and the tunnel broker methodology, we need to fill in a form that will, with a server, that will give us an IPv6 and IPv4 address at the end. Here, we don't need the IPv6 address. It's derived automatically. And the other thing that's automatic is that this prefix is reserved, 192.88.99/24 is reserved for 624. It means this is the IPv4 address of the IPv6 internet. It means that if I send a packet to any, in practice, only the .1 is used, as far as I know. If you send a packet to this, that means presumably it's an IPv4 packet that contains an IPv6 packet. And the intention is to deliver it to the IPv6 internet. So in order to create a tunnel here, all I need to know is this address, but this is a well-known address, so there is no configuration to do. So when this router has a packet to send and it's not local here, it will encapsulate it inside an IPv4 packet to this address, and through the normal business of IPv4 routing, it will reach a router that responds to this address. In fact, there will be many, many routers that will respond to this address. It's an example of what I call anycast. It's an anycast use of a unicast address. That's a unicast address syntactically. In IPv, we know there are multicast and unicast addresses. Those are the only two things that exist. But here, sometimes people say it's called anycast in the sense it's not the address of one interface, but there are many, many interfaces that respond to this address. We've seen this used several times. We've seen it in load balancing, for example. Load balancing servers will do things like this to multiple load balancer will have the same IP address so that you reach one of them through equal cost multipath routing. Here it's typically not equal cost multipath routing. but probably you will go to the shortest of these. Now, the B is called a 624 relay router. So it's a router that accepts to be the endpoint of tunnels. It's a complicated word for saying there is no physical tunnel that's built. It just means whenever a packet comes to this destination address, it removes the IPv4 header and does the normal job it would do as an IPv6 router. So this is how 624 works. In fact, 624 is deprecated today. Deprecated means it's considered not good practice to use it. You can still, it still works, you can still use it, but it's considered not good practice. The main reason is that when operators starting to deploy this, they saw a lot of problems. Essentially, the use of these anycast addresses here. It means that if I am a very aggressive deployer of this solution, I will deploy a lot of those 624 relay routers. But anyone in the world who's using 624 might end up coming to me, which is perhaps not what I want. If I am Swisscom, I want my 624 relay routers to serve my paying Swisscom customers, not Sunrise, who is a bit cheaper and might deploy 624 by sending all this traffic to me. That's certainly something you do not want. It's similar to the hot potato routing issue we saw in BGP. Providers typically want to have more control on their volumes of traffic. Some providers want to avoid that cheap providers use them as free riders. Sometimes it's the other way around. If you are Sunrise, perhaps you don't want your traffic to go to Swisscom because you don't trust Swisscom. Perhaps you think they are less good than you. At least they don't provide as good an access to some YouTube servers, some games, etc. So you want to make sure it goes to your 624 relay service. So it can be one way or the other, but the conclusion is always the same. As a provider, you don't want those well-known addresses, this well-known block, and this well-known also way of mapping an IPv4 into IPv6. So this has been addressed by having a variant of 624, which is called 6RD, which is exactly the same, except that the blocks here are not universal blocks, but they're provider dependent. If you're Swisscom, you have an IPv6 block and you have an IPv4 block. So you will use part of your IPv4 block for this here, for these addresses, a bit like we do with the configured tunnels. And you will also use part of your IPv6 block for providing this IPv6 extension for IPv4 customers. You can, and those are blocks that are done privately, so it's not necessarily published what are the prefixes. You can test whether you're using 6RD, because typically you will see that your IPv4 address here appears inside your IPv6 address. So if you find a way to go into the IP addresses of your modem, you will know its IPv4 address, it's IPv6. If you recognize the IPv4 in IPv6, it's very likely that your provider is using 6RD. That's the deployed solution in many places where a provider has a legacy, has been deploying its infrastructure 10 or 20 years ago. 10 or 20 years ago, nobody wanted to deploy IPv6, so they deployed IPv4. Now, if they provide, it's a way to provide IPv6 quasi for free without redeploying an IPv4 internet. There are even worse cases. So that works if you're able to deploy 624 in your ADSL modem. So it's typically not you who does it, it's Swisscom or Sunrise, your ISP does it for you. There may be cases where you don't have IPv4 at all, IPv6 at all, and you are behind a NAT. So if you're standing behind a NAT, the 624 solution will not work because the NAT will not understand what is happening here. So there is an alternative to that, which is called Teredo, which we will not discuss in detail. It uses another address block, 2001 0/32. So such addresses are always Teredo. Some versions we may use in Linux is called Miredo. It's been deployed by Microsoft, believe it or not. Windows was pioneering here, and Linux came second in this exceptional case. And it's like 624, it's experimental. It's not even longer supported by Microsoft, but it's supported by people who deployed it in Linux and continue to give the relay, the 624, the IPv6 to IPv4 relay servers, which are called Teredo relays. And like 624, it works, or like tunnels, it works more or less good. But the benefit is that it's just software that you deploy inside your Linux machine, and that gives you IPv6 access without having to do any configuration of tunnels of any kind. Those are the, I would say, the existing solutions for encapsulations. There are other problems that are not solved entirely by encapsulation, and in particular, interworking. So encapsulation is helpful for like-to-like access. Here is another an example, which uses a different type of technology. No, sorry, it's also like-to-like access, but now we have the converse problem. The converse problem is you have IPv6 only. Why do you have IPv6 only? Perhaps because you're in a region in the world where there has been a lot of growth compared to when the technology was deployed. So typically in Asia and Africa, you have lots more IP addresses that are being deployed today than 10 or 20 years ago. So operators typically don't have enough blocks of IPv4 addresses to do the job. So they deploy IPv6 only. And we hope that in a not so distant future, that will be the standard case, even in countries where there is a legacy of networks that were deployed, like here in Switzerland. So assume you receive only IPv6, but you want to run IPv4. Now you could say that's a bit stupid, because if the problem is on me, not on the network, I can fix it easily. My smartphone, my PC, probably has IPv6, unless I have an old thing that I have not updated for many, many years. So it's easy. You simply, the answer would be do a software update, which you should do anyhow, because otherwise your system will be infected, probably will have security problems. But that doesn't solve everything, because there are still devices that are very hard to update. For example, a telephone in an elevator, perhaps an old style printer somewhere that still does some specific printing for you and works only for IPv4. And also the zillions of lines of codes of systems that works only for IPv4. One of them, for example, is InfoScience and Google Scholar. For some reason, they don't work on IPv6. I don't know why exactly, but I guess it is because a lot of the authorization access rights to online libraries use IPv4 addresses. For example, EPFL has a subscription to the digital library of ACM and IEEE. And I guess that the way this is done is by recognizing that your source IP address is belonging to the block of EPFL addresses, 128.178/15, right? So if you're not on such an address, you need to start the VPN and then it works. So, and now they do it only for IPv4 because the people who do that are not yet aware of IPv6. Surprisingly, even Google Scholar has this problem, which is more surprising coming from Google. So the take-home message is at the end, there will still be IPv4 only applications that you want to reach. So one solution for this is called this complicated name, 464XLAT. X means cross or translation, I guess, in English. So it means translation from 4 to 6 to 4. And we start IPv4, we translate to IPv6, and we translate to IPv4 again. That's also a solution that's very much deployed and will probably continue to be deployed in the coming years. So it's probably necessary to understand how it works. The details are easy, at least in one direction, and in the other direction, the difficult direction, we know already. So assume you want to support IPv4 to IPv4 over an IPv6 connectivity. Then we put a box called a CLAT, Customer Address Translation, that will translate your IPv4 addresses into IPv6. Now, it works, since we translate, we can very well have private addresses here. How do we do this? Well, we need some cooperation from your provider. The provider in this solution needs to do something, which consists in giving you an IPv6 block or an address here. That's the block that is provided here. That's a 96 blocks. /96 means there remains 32 bits for the host part, which will be used for in those 32 bits. We can put an IPv4 address here. So this block here is given to this customer. It's not a generic block. It is just to me. My home installation receives this block here. Then there is one block of there is this block. This block here is given for this customer. So that's my IPv6 block. I need a bit more because I want to build an entire network here with several subnetworks. And there's another block here, which is contrary to what I just said a minute ago, which is global. It means this is the IPv6 address of the IPv4 internet seen by this provider. It's a bit like the address block that we had in 624, but it's a different one here. And the block has 96, means we can input an IPv4 address in each of those here. Similarly here, in the IPv4 internet, we need a block of addresses, for example, this one, which means the IPv6 internet seen from IPv4. So those are the 3 blocks we can do. Now, given this, there's something that's very easy. The CLAT, we can think of it as a NAT. What does a NAT do? A NAT translates private addresses into public addresses, but typically a standard NAT translates IPv4 private addresses into IPv4 public address. The same happens for IPv6, though it's less used. Here, it will not translate an IPv4 into IPv4, but an IPv4 into an IPv6 address here. So, for example, if I have a device that responds to the address 10.1.2.3 here, then it will be translated to an address which is within my block here. So within the block, the block is a bit larger. I need to reserve a space, for example, by padding zeros everywhere, such that this is my translation of this address here. You recognize in green here, A is 10. So this is 10.0.1, 10.1.2.3. So that's the hexadecimal notation of IPv4 addresses. If IPv4 would be invented today, this is how we would write IPv4 addresses here. So that's the normal job of a NAT. When this sees a flow going on the outside here, it will replace the source address by this one here. Now, contrary to a NAT, there is no need to fiddle with the port numbers, because before, a standard NAT has a problem of collision. You have multiple private addresses on the local side and perhaps one single public IP address. You need to put all those many addresses into one. And it's impossible unless you find another field to make the difference, which is the port number. So we fiddle with port numbers in a NAT. Here we don't need to do this. So in this direction, we don't need to fiddle with the port numbers because the space of IPv6 is large enough to contain all my IPv4 space. So there is never any collision here. So that is what is happening in this direction here. And similarly, if I have, that's for the source address, if I have a destination address, so this guy is sending a packet to this guy here, the destination NAT.8.7.6 also needs to be mapped to an IPv6 address. For this, we use the prefix. That means the IPv4 internet seen from IPv6 from the viewpoint of this ISP here, which is this block here. So we will add the IPv6 address in this block, and that gives an IPv6 address. So we see we have an injection of IPv4 addresses using different prefixes inside the IPv6 domain here. So in this direction, everything is easy. That works well. On this part here, of course, it's not so easy because on this part, we have IPv6 addresses that need to be mapped to IPv4. IPv6 is very large. IPv4 is very small. So we have exactly the problem we had with a NAT, where a NAT has to map a large number of things into a smaller things. So we do exactly this. In fact, it's what is called the PLAD, the Provider Address Translation Device, is a NAT. It's also called a NAT 6.4. network address translation. It translates an IPv6 packet into an IPv4 packet, which means translating the header, replacing hop limit into TTL, etc. And also mapping the address here. Well, it's time to do a break. So after the break, we will see how this translation is done. So let's try to analyze this complicated scenario where I have IPv4 packets sent from the host on the left, H1 to H3 here. So the source is 10.1.2.3, the green IPv4 address. The destination is the blue address. We've seen what happens on the left here. On the left, we embed the source address into this prefix here, and we replace the destination address by something that is complementing this prefix there. So we have two ways of embedding the IP address, depending where it's expected to be. Now, what does this machine do? It receives a packet, which is an IPv6 packet, that needs to translate it to an IPv4 packet. It has two translations to do, the source and the destination address. For the source address, there is a problem, which is the usual NAT problem. The source address is the green address here. That needs to be translated into a blue address. But it's impossible because the scope here, the range of addresses that exist is much larger than the addressing size of the IPv4 internet. There can be as many green networks as there are such prefixes here. And since the number of IPv6 such prefixes is very large, this is a larger domain than can be mapped. So we need to do the regular NAT stuff. So we will map this address to an address that is a blue address in this block here. The 100 block has been mentioned several times. This 100 block is used for carriers to do carrier-grade NATs. So we'll map this address to, for example, that one. And since there are not so many blue addresses, it will also take the port number to expand the number of blue addresses artificially here. The other address is easy. When we had to translate the IPv6 address, destination address to that, well, that is easy because the 9.8.76 was already contained in this. So that's a stateless address translation here. So like any NAT, this provider address translation device needs a NAT port table. So it's in fact a carrier-grade NAT, and it is a major performance bottleneck for such solution and a cost issue also. Such a high-end machine with high performance will be an expensive one, but that's an object that is part of the transition from IPv6 to IPv4. We cannot avoid it. So let's test our understanding on this little quiz here. I close the poll. Closing. The answer is B, which is also the majority vote. Here, there's no encapsulation. We are in the IPv4 internet. There is no encapsulation. The name translation means exactly this. So seen from the IPv4 internet, we're talking to somebody who is on IPv4. Not, we don't see encapsulated packets or whatever, which is the goal of this solution, right? Is to be able to speak to something that is natively IPv4. The problem is not to transport an IPv4 packet over IPv6. It is to speak to somebody who can do only IPv4. So that's the answer. Now let's continue. If we do the Wireshark at this point here for the same thing, what is now the answer? I'm closing the poll. And the majority says B, which is only partly true. The IPv6, the correct answer is B and C. The IPv6 destination address is the mapped address, mapped with this prefix here that's specific to Homer's installation. So that is correct. And the source address, which is the IPv4 address of this host, which is a host that does not even know that the world has IPv6 somewhere, which is mapped using a universal prefix, at least universal in the domain of this IPv6 provider, which is the way to map anything IPv4 into this here. So we see incidentally that this solution, which starts to be deployed and will probably be deployed a lot in the future, is supporting private IPv4 addresses in a very efficient way, at least seen from the customer viewpoint. From the provider viewpoint, there is a cost of maintaining a set of devices like this one here, but providers are happy to buy hardware and sell services. It's their job, so that's not so much of an issue. And hardware providers are happy to provide hardware, that's their job. So Juniper, Cisco are happy to build such machines here. And we see that paradoxically, such a solution might well make IPv4 private addresses very attractive. In fact, if you are running something here, if you get IPv6 from your provider, all you need is that the provider supports this PLAT end of the system, and then you can continue being IPv4, and even better, you can have your own IPv4 address space and communicate with other people in the world who have also the same thing here. Because what we have not shown is, of course, we can communicate from one such thing to another thing because we will have different red prefixes for the different CLATs here. So in some sense, this intermediate solution extends the attractivity of the private IPv4 addresses, which we observe in practice. In particular, for example, you take the smart grid project at EPFL. After 1 or 2 years of trying to do it with IPv6, eventually I was unable to convince the electricians to continue working with IPv6. So everything that is being done and is new and is being deployed today is done with IPv4 private addresses here. It's bad news for IPv6, but this is how the reality is. Why is it? Well, because if you're not interested in networking, like we're in this course, but you have to use networking, like practically anybody who's working with robots, with smart grids, with any kind of automation, you need to do something that communicates, and whether you like it or not, you'll be confronted with addresses. You have to choose addresses for your robots, for your things, etc. Choosing IPv4 addresses is very easy, right? You pick 10 dot something. If you have a large network, you do 10.1 for the subnetwork 1, 10.2 for the subnetwork 2. That's very easy, trivial to use. If you use IPv6, we have seen that the IPv6 addresses have an IPv6 prefix of 64 bits, or 48, I don't remember. But you need to create first this prefix and add it to all the addresses you will have. So it's very verbose, very complicated to use in terms of addresses here. That's why perhaps IPv4 would survive for a very, very long amount of time, at least in private addresses space. We don't do encapsulation here, we do translation. What's the effect on the path MTU? I'll close the poll in a second. Majority says A, which was expected given my introduction, but is wrong. Now it's more tricky, it's more subtle here. The path MTU is the size of an IPv4 packet. So your IPv4 packet, assume it's 1500. That means you allow the higher layer, UDP, to create a content of 1500 minus 20, 1480. But this content will be this packet will be translated here into an IPv6 packet. An IPv6 packet adds 40 bytes of header, not 20. So your content plus 40 must fit within 1500. So your content cannot be as large as 1500 minus 20. It's maximum 1460, which means the entire packet, when you add the IPv4 header, will be 20 bytes less. So you need to make sure there is 20 bytes extra because your header will be inflated by 20 bytes again. This solution is used in another context for true interworking. Perhaps that's the most interesting deployment that we will see also to continue. So assume now I have IPv6 everywhere at home, because as I said, after all, if you control your own environment, you probably have systems that are not so old or up to date. If they're up to date, they support IPv6. So you have IPv6 here, so you run IPv6 at home, you're an IPv6 provider, but you want to talk to some InfoScience. This is the InfoScience of Angola that works only on IPv4, like all the InfoSciences in the world that I know. So we can reuse, in fact, since everything is IPv6 natively on the left, we don't use the translation that was here. We can simply continue to use this NAT 64, PLAT, and exactly the same thing will happen. I have here an IPv6 packet that comes. In order to reach an IPv4 address, I need to allocate a block, which is the same as before, to the IPv4 internet seen from IPv6 by this provider. So that here, Homer on the left believes that he's talking to an IPv6 host. He sends a packet, his software sends a packet using an IPv6 socket to a destination, which is the mapped address, which is given here. We take the prefix for embedding IPv4 into IPv6, and we complement it with the IPv4 address. So here, everything looks IPv6. Here, we still need to translate, and the translation is exactly the same as before, using the NAT and using port numbers to be able to reuse a number of the blue addresses several times here. So this is something that provides now true interworking. An IPv6 software using only IPv6 socket is now able to speak to an IPv4 server that has only IPv4 sockets, and this one will reply to the host here that it believes is one host with this blue address here. There is still another issue, but we're now familiar with the type of solution that can be used, similar to when we have seen another solution for interworking, which is with application layer gateway, and we've seen that we need to complement the application layer gateway with something in the DNS. The same is true here. How does this client know the IPv4 embedded IPv6 address of server 4? Because server 4 does not have an IPv6 address. It's not sitting at all on an IPv6 world, so it publishes in DNS, probably, its IPv4 address only. Well, for this, you need that the provider that gives you this IPv6 only service also provides a DNS service, a translation service, which has a name. It's called DNS64. It consists in simply taking the big table, when the DNS server has an IPv4 address here, it will map it into an IPv6 address, because this DNS server is coordinated with the provider, and it knows what is the red block, the prefix that we add to all IPv4 public addresses. For example, when the IPv6 host opens a socket to speak to that IPv4 host, it will ask for an IPv4 address. So using getHostByName, we will send the request to the DNS server. Now, the DNS server we've seen will recursively try to get it, but now it is one that is smart enough to know I need to give replies that are only IPv6 addresses. So it will, using the classical method we've seen last week, how a DNS server goes over the internet, going first to the root servers, then eventually to the servers of this university here. This one will, which must be able to have all kinds of queries. So it will get an A address. It knows now I have only an IPv4 address, therefore I will translate it. And in my cache, remember that a server typically caches the reply. Here it will not just only cache, it will translate it. It will translate to this record. So it will create a fake record that does not really exist in the DNS, but exists in the cache of this DNS 6.4 server. And whenever this client asks for it, it will get this as an IPv6, something that looks like a native IPv6 address, but is not here. So this is typically deployed by this ISP and is transparent to client 6. So those technologies, the NAT 6.4, the DNS 6.4, in fact, they make a complete solution to interworking IPv6 with legacy IPv4. If we put together all the things we've seen, we find that there's a number of mechanisms. Practically all of them exist in some form. Tunnel brokers, 6RD are deployed by installations that have a lot of IPv4 and want to give IPv6 access at very low cost. The reverse problem is installations that are natively IPv6 and wants to still give access to IPv4 will tend to deploy NAT 6.4, DNS 6.4, and application layer gateways only in the last resort when there is nothing else that you can do here. So for example, if you're a mobile operator, you might be forced to launch an IPv6 only service, simply because if you ask for a block of 1 million addresses here, you're a Chinese operator, so you think in millions, you want to launch a service and you need 1 million different addresses, you will not get that from IPv4. In fact, you will get no address apart from extremely special cases, no new address for IPv4. So if you do something new today, if there is growth in your network, you will have only IPv6 addresses. If you're not new, if you're a Swisscom, you have a big block of IPv4 address that you keep and can reuse. But if you're a new entrant into that business, you will get only IPv6. So then you will be forced to deploy these 464 XLAT solutions, including the DNS 6.4. Now, how on the mobile, on the handheld device, on the customer device, if you have an Apple device, then Apple has been mandating for long that all apps should work natively with IPv6. So if you want something to be deployed on the App Store, it must work with IPv6. So you solve part of the problem. Android is a bit heterogeneous. Android supports IPv4 apps and puts the CLAT in the device. So an Android mobile can, not Android versions have it, but the high-end versions will have the CLAT device. And certainly if it's deployed on an IPv6 only service, you will need it. So that will allow you to have some apps that work only with IPv4 and will speak to IPv4 servers. For a long time, that was the case of Skype that was somehow reluctant to deploy IPv6. So those are the things we will see and continue to see, unfortunately, in the long term. We wish we never had this, because IPv6 would be just a superset of IPv4, but it is not. Therefore, we will have to see all those things. Voila, that's the end of this section 14. And now in the remaining 26 minutes, we will discuss of something that we have already alluded to when we spoke about BGP, and is in fact probably carrying the majority of traffic on the internet, which is MPLS. MPLS stands for multi-protocol label switching, and it is used in IP backbones of ISPs. It's also used, for example, at interconnection points. You remember we talk of May West, May East, Swiss IX, which are the places where multiple providers interconnect to each other. So those huge local area networks, some of them use MPLS here. It's used also, for example, in smart grids. The networks of electrical companies, which are large long-distance networks, use MPLS. It's not visible because there is no ping MPLS, so there is very little software that exists, although there is some. We can install on Linux MPLS software, but it's not so much known. Therefore, it's also more secure because much fewer attackers spend resources on attacking MPLS networks. And as we will see, it is fundamentally secure in the sense that it separates networks here. And it is a replacement to tunnels, or some people say that an MPLS is providing tunnels. But the major difference is that it does not use the principles of IP addresses at all. It uses the principles of what is called circuit switching or virtual circuit switching, also called connection-oriented network layer. A connection-oriented network layer is imitating something that probably your generation has not even seen, which is a standard telephone. Today, the telephone is an IP application, but 20 years ago, the telephone was a dedicated network with circuits. What were you doing when you were calling somebody by telephone? Where A, when calling B, you would dial the numbers, and this was translating into a message using a system very much like, think of it like SDN, for example. Your telephone was sending a message, or by dialing at the end of the line, there was a sensor that was sensing the numbers that were sent and was translating that into a message. And this message would go from telephone switch to telephone switch to open the circuit, the green or the red circuit here. That was in the case of telephony, and the circuit was like a 64 kilobit per second channel on which you put the voice. That's the last generation of telephone. The previous generations were even analog circuits, where the switches were physical wiring system, where you would, if you look very old movies, you see the ladies, typically those are ladies that are in the switchboards where they put jacks into sockets to put the connection. So that's the telephone network. This system is inspired by the telephone network. How is it inspired? Of course, we don't have sockets, we don't have 64 kilobits channel. It's all packets like Ethernet or IP packets. But the principle is that we use labels. So if I want to establish such a virtual circuit, let's call it in this way for a second, from A to B, I will use SDN or signaling or whatever protocol to speak to the switch and say, I want to open a connection to C. You can give the IP address of C or the telephone number of C or whatever way you have to identify C here. Then this will use some software to compute a route. For example, OSPF is used for that. But now it's not a use of OSPF like we do to populate the IP forwarding table. It is to decide where to go. Here, perhaps shortest path, but we've seen that OSPF is very flexible. It can compute not just the shortest path, but perhaps the path with a smaller delay or with a higher capacity or with at least enough capacity to establish this. So it will decide, for example, that I should go to S2 on port 2. But it will remember this in the form that is given here. This form is called a label switching entry. A label switching says that anything that comes in on input port number 3, input 3, with label 2 here, should go out on output port number 2 with possibly another label. Here the label is the same, but sometimes there are collisions and you need to change the label here. Now, if we follow this, when we arrive at this switch, on input port 1, anything that comes with label 2 should go to output port 3 with label 1 again. And why label 1 here? No, not again. Here we see that the label has changed here. Why may we need to change the label? Because the scope of a label is local. There are different versions of MPLS. The version of MPLS that's most widespread today considered that the scope is local to a node. So label 1 means something to node S2, and it means another thing to node S1. It's like a port number that is local to a given machine or a given IP address. A given port 53 on this machine identifies this DNS server process. On another machine, it identifies another process, and they are different, even though they have the same port number. Here it's the same. This label number is local. And the path is created by the concatenation of the values of all the labels here. We see there are two paths here, and the red and the blue go different directions. Why do we do this? Well, this imitates exactly this circuit switching principle, and the major motivation to continue to do it today is to be able to reserve resources along the path. While we do this, we could do something that we will not discuss in detail, where we might decide the green path, we allocate 1 megabit per second to this path. We've discussed, when we discussed congestion control at the end, we discussed there are things like deficit round robin, there are schedulers in Linux, in nodes, that can decide to allocate a certain bandwidth, a certain bit rate to some flows. Well, that's exactly a use case for this. So not only we decide on the label and a route, but we might also allocate to this some minimum bandwidth here. For example, the green would have 1 megabit per second, and the red might have 100 megabit per second here. So this is the background. MPLS was originated in this background, which, as you see, is very different from IP. IP, we don't allocate bandwidth to flows. In fact, routers don't see flows. It's only the NATs that do something with flows, but a standard IP router doesn't see flow, it just see destination address. Here, the intermediate systems, which are still called MPLS routers or sometimes MPLS switches, they see the flows. And since they see the flows, they can also manage them in a smart way. And this is, for example, if this is used to interconnect two VPNs, two networks here, you can allocate 1 megabit to this guy because they pay for a small subscription, and 1 gigabit per second for that other guy. So you can sell whatever bandwidth you want. So this is one of the mechanisms used by providers to create private networks over their global infrastructure. A major difference with IP is also that the table lookup is exact. Here, there is no longest prefix match or something like this. When something with label 2 comes here, you need to go exactly to the unique entry that has label 2, hoping that there is one. If there is not, it's a failure. The path, the label switch path was not created here. So that's also a very different difference compared to IP. In practice, if we do a Wireshark, we can still work with the MPLS. MPLS header is coming immediately after the Ethernet header. Sometimes people call it layer 2.5. It's between MAC and IP. An MPLS header contains the label. It contains also a quality of service because, as I mentioned, MPLS is typically used in context with bandwidth allocation. So one way is to allocate to every MPLS label switch path a certain bandwidth. A simpler way is to simply have multiple priority levels, which is possible with 3 bits here. And a TTL, for the same reason as we do with IP. There is an MPLS TTL, which is called TTL. It's not a time to leave, it's a hop limit, like in IPv6, which avoids loop or will kill packets if there is loops. And there is a bit, a flag, which is called bottom of stack, which is used to indicate the fact that, in some sense, it's a pointer whether the next header is again an MPLS header or not. In what I've explained, you expect to have only one MPLS header. But as we will see, we typically have 2 and often 3 MPLS labels. And I will explain why in a second. So this is used to know whether this is the last label. When the bit is 1, it means it's the last label, which means the next thing that comes is what you would normally expect after an Ethernet header. Here is an example that's explaining a typical use of MPLS by providers. That also explains why we may need 2 labels here. Here I'm showing a provider backbone that has on the left here, so all the cheese boxes here are MPLS routers. MPLS comes as a software into a router. So an IP router, the one we buy and deploy here at EPFL, does not support MPLS. But if you're a carrier, if you're buying a carrier router, a router for ISPs, for Swisscom, for example, you may install MPLS on it routinely. It comes as a default installation. It will have MPLS and IP. It does the two. It does IP forwarding and MPLS at the same time. We still do a distinction between what is called label edge router and label switching router. A label switching router does only what I presented on the previous image. It looks at the incoming label, goes into its table, and uses this table to know where to send the packet and possibly change the label here. So for example, here is what this router N would do. Anything that comes with label 34, for example, that comes presumably on this port C, the table says, change the label to 49 and send it on A. So this is the job it will do here. Typically, such tables are not huge. You don't have millions of labels, but perhaps thousands that correspond to the number of virtual private network that you're supporting over your carrier infrastructure. So this is the label switching router. That's the easy part. Now the label edge router does the same thing, plus it serves as an interface between the non-MPLS world, the world that we've analyzed for almost the entirety of this course, and the MPLS backbone. And here I'm showing a label edge router that has 3 customers connected to it, which use private IPv4 addresses here. And even we see that 2 customers, the green and the blue, use the same IPv4 addresses, which you expect, because that's the purpose of those private addresses. Anybody can use them. So now if you're the provider carrying this traffic, you should not make the assumption that different customers use different blocks here, but the users do whatever they want. And we will see in a minute how they can really do whatever they want, and the provider does not even need to be giving authorization for using a block here. But now, how do we carry a green packet to this green packet to this other side of the world here, where we have, again, another private address here? So imagine this is EPFL here in Lausanne, and this is PFL in Sion, and the private address parts of EPFL. How do they go over MPLS to the Swisscom infrastructure? Well, for that, we use another label here, which is identifying the customer here. So for example, the blue private network here is associated in A with the label 78. So any packet that comes on one of the ports that is identified with this customer is first tagged with this label 78. Then we add another label, we will see based on what, that is used for forwarding this packet through the infrastructure to the correct destination. So a packet that comes from this part here will have label 78 that identifies as blue, and level 49 that identifies that it should go this way. In this router, only this label is analyzed, because how do we know that only this label should be analyzed? Well, because the label switching table says, if you see label 49, this one here, the only thing you should do is change the label to 123 and go to port A. End of the story. So you replace this label by this new version, 123. Same thing here. When you arrive here, you replace it by 50. So at the end, this packet will arrive with a label 50. So the outside label has been changed. It's used for routing, for forwarding the packet. The inside label has not changed. And now at this router, we'll have an instruction that we will see in a second. This is the final router here. The label swapping table is a bit more sophisticated in a label edge router. It is saying which action to take for each label. In a label switching router, the actions are very simple. You simply change the value of the label and you forward the packet. Here you may do different things. For example, if the label is 50, the action is pop. Pop means remove the label, delete the label, remove the label. Remove the label, and then that was the outside label. What remains is the inside label, and the inside label was identified the virtual private network, which was 78. So I remove this, and we do something that we're familiar with, recursive table lookup. Once you have gone through the table to do something, you do an action, and then this action, this table should say to you whether you need to continue or not. If you pop, obviously you need to continue. So here you continue, and you look for an exact match. You will find the match with label 78. You remove the 78 because a packet that comes here with label 78 is a packet to be put on one of the output ports. Now, which output port? Well, we use the virtual routing table of what is called virtual routing function 2. Virtual routing function 2 means that inside a router, in principle, we have one routing table, one that contains IPv4, perhaps another one for IPv6, or they're in the same table. Here we have one routing table per customer, but they're all put in the same table with one attribute that identifies which customer it is. So this customer is called the VRF, virtual routing function value. So VRF equal 1 means green customer. So if a packet comes with label 49 here, the label will be removed. The inside label hopefully is 24. And if you find label 24, then you should go to that part of the table that has VRF equal to 1. And then it's like a standard IP table. If the destination address is this, then we go into the output port E with the next hop is that. The next hop will be used to find what is the MAC address using ARP, etc. So this is how we can combine the different virtual private networks, transport them over the infrastructure here, and go to remain in the same network. So the green, the blue, and the red private networks, they do not interfere other than in queuing here in the nodes here. But if you do a ping from a red machine here, it will be impossible to get anywhere to a blue if the ISP infrastructure is not corrupted here. Of course, the only way to do this would be to corrupt those tables here by changing the VRF. But from this, you need to gain control of the LER, label edge router. This is used quite a lot to solve one of the problems we had with BGP. We've seen that the interworking with BGP normally assumes that you redistribute BGP routes into your IGP, into OSPF. But that in some sense is a bit stupid because you have probably, we've seen in BGP, there's 1 million internet prefixes for IPv4. So you redistribute 1 million prefixes into a routing system, OSPF or a RIP or whatever you have internally, whose goal is to manage the connectivity inside your network. Your network has perhaps 50, 100 routers, seldom more. Very large networks have 1,000 routers. So you have perhaps 20,000 prefixes in total. That's the complexity of your routing system. But the complexity of the outside is huge. So we've seen ways to avoid that. And one way is to use tunnels or to run BGP everywhere. All of those ways are not very satisfactory. A very commonly deployed way is to use MPLS. So if I take this example again, assume here that I have an internal router that is not running BGP. We've seen one solution is to have it run BGP. And the problem is, how does a packet that comes from this side know at R1 that this destination address needs to go towards R6 without having to redistribute all the prefixes in the world into R1 and all the interior routing protocol? Well, the solution, if you think about it, the solution of tunnels is very simple, and that's the only one that's really scalable and makes sense. Because when we traverse this domain here, we always go to an external link from an external link to another external link. So the complexity of the going through across this network is only, the complexity is n square, where order of n square, or n square is the number of external attachments that you have, which is typically way smaller than 1 million. So what you can do is for any next hop that you know, that you learn by eBGP, you create a label switch path to any other next hop. So for example, when router R6 learned by eBGP 222, a route that has next hop 222 and accepts this route, it will create a label switch path by using SDN or whatever mechanism is used inside this domain to create paths that involves creating a label switching entry into R1. And then, for example, the values are 34 and 93 here. And that means that whenever a packet comes from R4 to this destination, 18.1 here, R2 from BGP will know the next hop. And at R2, there will be a next hop 222. Then R2 is now MPLS router. So it will have a table that says, whenever, how do I reach 2222? Well, I don't send it to a next hop like I would do normally. I push the label 23 here, and I send it on the corresponding port. So we modify the way of operating here, but that's the standard modification that all MPLS routers do. And the interest is, of course, that LSR1 will simply see a label 93, and all it needs is to know what to do with label 93 or the incoming label 34, 23, etc. So this is a very common solution for BGP, solving the problem of scalability of BGP inside the domain. I will conclude with this last thing, which is again an interaction with the BGP and MPLS, which is radically different. Here, the problem is not to solve the problem of distributing BGP information into my domain. Here, the problem is back to the example I had before. I had 3 different private networks that are interconnected to my provider, to Swisscom here. And now I need somehow to know who is connected, who is doing what. For example, this network is perhaps EPFL Campus. Itself has a number of subnetworks, a number of routers, etc. And this LER needs to know that in order to build the table that we've seen before. We can do that by configuration, but it would be better if we use a protocol for that. And the protocol that is used for that is BGP. So even though I am a private customer running through a public operator, I can use BGP. There is an extension of BGP that is using what is called a route discriminator attribute that supports this, which makes sense because BGP is done for that. It is done for one network to speak to another network and give information on what is available or not. So that can be used for passing the information to the provider. And beyond, we will use BGP here. So the green customer will send, for example, a BGP announcement saying, I have a prefix 10.1 and the next hop is 10.11.1. And for this, we need a private AS number, which is whatever number here. That's something you will never see on the internet. EPFL will never appear as an AS, but for switch, that is for Swisscom, who is doing that, there will be a provider number here. Then inside the provider, everything is following the usual BGP story. So I receive this information. This information is used to set up the tables locally into this label edge router. That is the injection of BGP information into the forwarding table, normal work that the BGP router does. And then through iBGP, I will inform all the BGP routers that support this MPLS VPN BGP of this message that I've received. So this message here will be passed to this router here. So this router will receive this information here with another attribute, which is called a route discriminator. This is the BGP way of saying this is the green VPN. So what BGP is, so this route discriminator means it is a completely separate addressing scope. So with BGP, normally there is IPv4 and IPv6, and 2 IPv6 addresses cannot be the same. There is not an IPv6 address for EPFL and another one for Nestlé, and they are the same address, and they don't correspond to the same machine. That is not possible. IPv6 is global, IPv4 is global. Here with route discriminator, whatever is under the scope of route discriminator means it belongs to a special IPv4 world. You could even give public IPv4 addresses here, but typically we don't do it. Good practice is to use only private ones, but you could do it. So that means BGP will treat all the different values of route discriminators as different networks that don't communicate with each other. But they will communicate within this route discriminator. In particular, router B, BGP router, speaks BGP to the second half of the green customer, and the BGP router and the green customer will receive the information. There is a 10.1.16 next hop with a given next hop here, and the next hop will be something that is local here, so that now the green customer will know where to send packets that go to this destination. So using this mechanism, the IP structure of the private network will be entirely deployed through the different sites and in a completely automatic way. This is why it is called MPLS VPNs. So it's VPNs that use MPLS for their automation. And providers like, I don't know about Swisscom, but French Telecom, Orange, the last thing I read is that 90% of their traffic is in this, of that type here. So in fact, interconnection of private networks is the largest volume of traffic, at least for some providers today. Mm-hmm. I will conclude and steal 2 minutes of your time to conclude on this, is that the labels can be used also inside labels to do something that is obvious but very useful to gain scalability. This is what we discussed before. We had label edge routers that communicate, that help several private networks communicate over a public infrastructure here. But when you do this, it is very often the case that you have a lot of paths that go towards the same place. So you might have, for example, a lot of paths in Lausanne that end up in Zurich here. So if you're Sunrise or Swisscom, you have a big switch in Lausanne, a big switch in Zurich. You don't want necessarily to build a separate path for everything from here to here. You can put them in the same tunnel or in the same label switch path if the quality of service allows it. And that will make those routers here much more scalable. If we look at what will be done here, when a packet comes here, we look at the outer label, label 50, and the label 50 will be swapped to label 34. So all the different packets that go from Lausanne to Zurich have the label 50 here and follow the same path. At the end, when they join Zurich here, then we will split them and they will be deployed to different parts of the city using different label paths. So the label path can be stacked for scalability to make a hierarchical structure that makes it way easier to manage. Voila, that's the end of this module, where we've seen things that are a bit less typical of the internet, and but are still existing and are important, at least for carriers. That's the end of this course. So I wish you a Merry Christmas, and we will meet again in January, in perhaps less pleasant condition for you, at least. So thank you very much. It's the last lecture of this course. It's also the last lecture of this course for me. It's the last time I'm teaching it, because I will be retiring next July. So I would like to thank in particular all my wonderful TA team for making this course so smooth, and I hope you enjoyed it. Thank you very much. Thank you.